So last class session, we discussed carbonyl substitution reactions and we discussed the relative reactivity and naming conventions of different acyl group and carboxylic acid derivatives. Generally, the better the leaving group on your carboxylic acid derivative, the more reactive that carboxylic acid derivative is to carbonyl substitution reactions. What we're now going to do is we're going to cover the general mechanisms for carbonyl substitution under acidic and basic conditions, as we'll see this general mechanistic pattern repeated throughout this chapter. So let's look at the basic mechanism for carbonyl substitution. First, your nucleophile is going to directly attack the electrophilic carbonyl carbon. From here, we'll generate a tetrahedral intermediate, which will then quickly collapse to kick out our leaving group. This regenerates our carbonyl and our stable carbon-oxygen double bond and generates our desired carbonyl substitution product. Although this reaction is technically in equilibrium, usually the nucleophile and leaving group are chosen to ensure complete reaction and minimize reverse reaction. So generally use a strong nucleophile and your leaving group is generally going to be a weak nucleophile, part of why the leaving group is a good leaving group. Does this general mechanism make sense to everyone? Okay, so let's look at carbonyl substitution under acidic conditions. Keep in mind, under acidic conditions, our nucleophiles are appreciably weaker because they're protonated. As such, before we see nucleophilic attack onto the carbonyl carbon, we first are going to activate our carbonyl for nucleophilic attack via protonation. As we notice, looking at this resonance structure, the carbonyl carbon now has a substantially increased amount of cationic character and is overall more reactive to nucleophiles, even weak protonated nucleophiles. From here, your nucleophile will attack the electrophilic carbonyl carbon. We generate a tetrahedral intermediate. However, in this case, we have to activate our leaving group. To do that, we're going to engage in a series of proton transfers in which our leaving group is protonated and our added nucleophilic species is deprotonated. From here, we now have our tetrahedral intermediate primed to collapse and kick out our leaving group. So we'll do just that. We'll kick out our leaving group. And then from here, all we have to do now is pull off a proton, be it with water or even an equivalent of the conjugate base floating around. Really anything will do the trick as long as it can accept a proton easily. And that gives us our desired acyl substitution product. Does this general mechanism make sense to everyone? Any questions on this mechanism? Okay, so Let's talk a little bit about general reactions of carboxylic acid derivatives, and let's talk about probably the most easily diversified carboxylic acid derivative, which is the acyl chloride or acid chloride. These are really great starting points for acyl substitution and carbonyl substitution, as due to their substantially great reactivity, these acyl halides and acyl chlorides can react with a range of nucleophiles to generate a range of carbonyl derivatives. One thing to note, acyl halides are quite reactive with water and other nucleophiles, so they're either generated neat or in an aprotic non-nucleophilic solvent. Just as a refresher, thionyl chloride is quite a useful reagent to prepare acyl chlorides from carboxylic acids. And once we have this acyl chloride, we can react it with essentially any nucleophile we want to generate a carbonyl derivative. Does this idea of the acyl chloride as a useful starting material make sense to everyone? Any questions I can address? Okay. So let's try to apply what we've learned now. And in this case, we're working under neutral to slightly basic conditions. And I'd like us to predict the product of the following reaction and draw a mechanism for this reaction. So in this case, we have an acyl chloride and an amine. What is going to happen? So we have a nucleophilic amine, electrophilic acyl chloride. Let's take 3 to 4 minutes to work through this example, and then I'd like students to share their proposed mechanism in the chat, verbally, or annotated directly onto the class whiteboard. And if there are any questions that I can address to help advance our discussion, of course, don't be shy to ask them in the chat or verbally. So would anyone like to share their proposed mechanism, either annotated on the whiteboard or as a photo in the chat? So we have a nucleophilic amine, we have an electrophilic acyl chloride, and we're working under slightly basic conditions. So we're dealing with a carbonyl substitution reaction under slightly basic conditions. So what's the first thing that's going to happen if we have a nucleophilic amine and an electrophilic acyl chloride? So under acidic conditions, we'd see protonation, but under basic conditions, our amine is just going to attack our carbonyl carbon. So as students have noted in the chat, because we're under basic conditions, we have a basic amine floating around. The first thing that's going to happen is our amine will attack our electrophilic carbonyl carbon. From here, what's going to happen next? Oh, whoops, I skipped a step. So we have our tetrahedral intermediate. So what's going to happen next? Do we have a great leaving group? Do we have a great leaving group that we can kick out? So we have this tetrahedral intermediate. what leaving group are we going to kick out? Chloride, yep. So we'll kick down our carbonyl lone pair and kick out our leaving group of chloride. And that in turn generates our protonated amide. And in order to get a neutral isolable species, what's a reasonable base that we could use? What's a reasonable base that we can use? So what's a reasonable base that's floating around in solution for this last step where we deprotonate this amide? Yeah, the amine is appreciably basic, so our amine will pull off this proton, and that will give us our desired neutral amide. Now, this is important because this helps explain a common modification to the reaction procedure if you want to make an amide from an acyl chloride. As we notice, we end up using some of our amine in this deprotonation step. So the way these reactions are practically run are either by using an excess of amine, which can work, or you can use a stoichiometric amount of added base, such as sodium acetate or sodium hydroxide that we have seen previously used as a base to help quench the excess acid when we prepared acetanilide in the laboratory. Does this idea make sense to everyone? So looking at this mechanism, we've been able to identify that often a trace amount of basic additive, at least one equivalent, is needed to fully scrounge the acid generated over the course of this reaction. Does this mechanism make sense to everyone?
Oh, Professor, what is this that you have here? I can't see it clearly.
Oh, sorry, one moment. Let me. One moment. Oh, that's just showing the arrow where we're kicking the electrons that were in this nitrogen-hydrogen bond up to the nitrogen.
Oh, okay. I thought it did like a double arrow circle thing. I was like, what's going on? Thank you.
Yeah, perfect. Any other questions on this example? Any other questions on this mechanism? Okay, so let's keep going now and let's look at another example of these kinds of carbonyl substitution reactions under neutral to slightly basic conditions. And in this case, just to make things a little more interesting, rather than using this thiol as is, if we want to make a more reactive nucleophile, would we want to go with this neutral thiol or should we generate a derivative? What's a more nucleophilic version of this thiol? Should we go with the neutral form or the anionic form for a carbonyl substitution? We'd ideally want to use the anionic form. So let's look at what happens if we use the anionic derivative, which we can prepare with sodium hydride or any reasonably strong base. Okay, so we have an electrophilic acyl bromide. We have a nucleophilic thiolate anion. Would anyone like to try and draw out the mechanism for this reaction? Let's take a few minutes to work through this problem, and then I'd like students to share their responses in the chat verbally or annotated directly onto the class whiteboard. And if there are any questions I can address to help advance our discussion, don't be shy to ask them in the chat or verbally, and I'd be happy to address your questions. So, does anyone have a proposed mechanism for this carbonyl substitution reaction that they'd like to share? So we have our nucleophilic thiol derivative. Yes, this is under basic conditions, as evidenced by the fact we have an anionic thiol derivative. So under basic conditions, what would the mechanism be for this carbonyl substitution reaction? Would anyone like to try annotating the mechanism on the class whiteboard or sharing their thoughts or a photo of their drawn mechanism in the chat? Yep, exactly right. Your nucleophilic thiol will attack your electrophilic carbonyl carbon. And from here, we'll make a tetrahedral intermediate. From here, your tetrahedral intermediate will collapse, and you'll kick out your alkyl halide to make your desired carbonyl substitution product. Perfect, perfect. The student proposed mechanism looks completely reasonable. So let's recap this mechanism as part of the instructor solution. So we have our electrophilic acyl bromide, our nucleophilic thiolate derivative will attack and generate a tetrahedral intermediate. From here, we're going to kick out our leaving group. And in this case, our best leaving group is going to be our halide. So when our tetrahedral intermediate collapses and we regenerate our carbonyl, we'll kick out bromide, which is a great leaving group. And thus we're left with our carbonyl substitution product. Does this mechanism make sense to everyone? And does everyone understand why using the anionic derivative of our thiol leads to a faster, more efficient reaction? Does that make sense to everyone?
Could you, I know you just said it like 5 minutes ago, but could you just explain again how, because Christine asked if it was under basic conditions and you said yes, and you said it was because we see the anion, like how does the presence of a base make it the anion?
So if we, generally, this anion, the conjugate acid pK of this thiol, right, is it's slightly more acidic than a typical alcohol. So we'd say it's somewhere around 14, right? This is the pKa of this thiol, right? So then this thiolate, by analogy, is going to be reasonably basic, correct? And
Yeah.
in order for us to have this thiolate present in solution, we can't be under acidic conditions, nor can we be under neutral pH 7 conditions. Otherwise, we'd protonate this thiol pretty quickly.
Oh, okay, that makes sense.
Generally, the presence of a basic anion implies we're under basic conditions.
Okay.
Likewise, the presence of an acid catalyst or an acidic species or protonated intermediates that are acidic would imply we're under acidic conditions.
Okay, that
Does
makes
that make
sense.
sense?
Yeah, thank you.
Sure. Any other questions on this example?
Yes, I have one.
Yes, please go ahead.
Can you explain again why the presence of the Na plus makes it faster?
The sodium is just a countercation, but if we have a thiolate, so comparing these two species, which of these two species are a better nucleophile? This protonated nucleophile or this anion? Generally, what's a better?
Anion.
The anion is generally going to be more nucleophilic, right?
Yeah.
Also, the anion similarly is a worse leaving group. So by using this anionic derivative of our thiol, the addition step occurs more readily. And when we're thinking about kicking out a leaving group, it's way easier to kick out bromide than to kick out this anionic species.
Okay.
Because remember, the generally poor leaving groups are strong nucleophiles and are strong bases.
Oh, okay. Got it.
Does that explanation make sense?
Yes. Thank you.
Perfect. Perfect. Okay, so let's keep going now. And let's try one more example. This time we're also under basic conditions. In this case, we're treating an acyl iodide with sodium methoxide in methanol. Let's take and apply what we've learned in the previous examples, and then let's try to draw out a mechanism for this reaction. So this time, are we under acidic or basic conditions? Looking at these reaction conditions, are we under acidic or basic conditions? Basic conditions. We have the nucleophilic basic species methoxide in solution. So, given these reaction conditions, let's try to apply what we've learned from the previous example, and let's try to draw a mechanism for this reaction. And if possible, I'd like students to share their responses in the chat, verbally, or annotated directly onto the class whiteboard.
Is it just gonna be the same, like substitution?
Yep.
Or
Yes.
Okay.
Yes.
I'll give it a try.
Perfect. Perfect. No worries. And it's mainly just to help develop the patterns for drawing out the arrow pushing mechanism and really showing how general this carbonyl substitution mechanism is. Because we've made an amide, we've made a thioester, now we're making an ester. So we can make a range of carbonyl derivatives from an acyl halide, and the mechanism is identical in all of these cases. And that's part of the idea that I'm trying to convey. Okay, so as the student's drawing out, our nucleophile attacks the electrophilic carbonyl carbon. We form a tetrahedral intermediate, which collapses to make our ester. Yep, exactly right. So as we notice, even though we're preparing a range of unique substrates, the overall mechanism for carbonyl substitution remains functionally identical. So just redrawing the student proposed mechanism as part of our instructor key. Our nucleophilic methoxide attacks the electrophilic carbonyl carbon. From here, we'll generate a tetrahedral intermediate. And from here, we'll kick down our lone pair and kick out our leaving group to make our desired ester. So as you can see, we've prepared a range of carboxylic acid derivatives from the acyl chloride, bromide, and iodide. Does this make sense to everyone? Okay, perfect. So let's talk a little bit about how we prepare these acyl chlorides and other acyl halide derivatives from carboxylic acids. Thianil chloride is a wonderful reagent to convert carboxylic acids into acyl chlorides. In terms of the mechanism for this reaction, let's talk about each step. First, you have your carboxylic acid, and thianil chloride has a highly electrophilic sulfur atom. Your carboxylic acid will attack your electrophilic sulfur atom, and interestingly enough, we'll see a mechanism that closely reminds us of carbonyl substitution reactions, where we make this highly substituted intermediate, which then collapses to kick out our leaving group. From here, we now have converted our alcohol into this wonderful leaving group. Can everyone agree that this chlorosulfonyl ester derivative, or this chlorosulfite derivative, is a pretty good leaving group? Does everyone agree how this circled group is a better leaving group than just this alcohol? Does everyone agree that this chlorosulfite derivative looks like a good leaving group? How we've now activated our alcohol as a leaving group? What do we think? If we had to pick hydroxide or this chlorosulfite derivative, which one would we choose? A or B? Which leaving group looks better to everyone? Just at a first glance.
B.
B, by far. And why? Why are we leaning towards B? What's special about it? We have one student commenting the group could better stabilize its charge, right? Also, what's attached to our oxygen? Is this sulfur group electron withdrawing or donating? In general, looking at this group, does that look electron withdrawing or donating? Electron withdrawing, right? So we're able to readily stabilize any negative charge generated if we kick out this leaving group. And further, this particular leaving group has another trick in that it also decomposes when it leaves. We'll talk about that momentarily. Okay, so now that we have activated our alcohol, we're now ready for our very strong nucleophile. Note, chloride is a pretty weak nucleophile under most cases, but when we have such an activated substrate, chloride will just go straight for the carbonyl carbon and will make a tetrahedral intermediate. What's interesting about this mechanism is that unlike 99% of the examples you'll see for carbonyl substitution, if we had to pick a leaving group to kick out, chloride or this chlorosulfite derivative, which of these two leaving groups would we kick out? Which of these leaving groups looks like the best leaving group? Are activated alcohol or chloride? The activated alcohol. This is one rare case where we actually have a better leaving group than chloride. And the reason why this leaving group is such a great leaving group is that it decomposes as the leaving group leaves. So this gives us our desired acyl chloride, and it also gives us some byproducts of sulfur dioxide and chloride. So the beautiful thing about this activated leaving group is that once it leaves, it's never coming back. It's decomposed and it's already escaped into the gas phase in the form of sulfur dioxide. So that further helps drive this equilibrium and drive this reaction to completion. So this is a case where substitution and displacement of this activated leaving group is highly favored by entropy because you're generating these gaseous byproducts when the leaving group leaves. Finally, as a last step, not water, but any reasonably basic species, even chloride will do the trick. We'll pull off your proton and generate your desired acyl chloride. Does this mechanism make sense to everyone? So in this case, just like other cases where we've displaced an alcohol, we're activating our alcohol and the carboxylic acid as a leaving group. The leaving group gets displaced via textbook carbonyl substitution reaction, and this is why we're able to isolate the acyl chloride efficiently, because we've activated the carboxylic acid, so we have a better leaving group than chloride. So even the weakly nucleophilic chloride can attack and displace this leaving group to make our acyl chloride derivative.
So you refer to it as an activated alcohol?
Yes.
So how is it an alcohol?
It's mainly just boxing in this group and saying, yes, this is part of a carboxylic acid, but I like to think of this leaving group as an activated alcohol, similar to a tosylate.
Oh,
And
okay.
that really helps us see that we can displace and lose this leaving group quite readily, as this leaving group is a pretty good leaving group because it can stabilize any negative charge, and as well, the actual carbonyl carbon is activated because you have this strongly electron withdrawing group attached to your carbonyl carbon. So yes, this is part of a carboxylic acid, but if we're thinking about a substituent in terms of, is it a good leaving group? Is this carboxylic acid derivative activated or deactivated? We start to look at the individual substituents and we start to assess, does this look like a good leaving group? And the answer in this case is yes, it's quite a good leaving group. Does that make sense?
Yeah, it does. Thank you.
Perfect. Any other questions on this example? Okay, so let's try to apply what we've learned. Here's another reiteration of the mechanism for the formation of acid chlorides. So in this case, our carboxylic acid will attack the electrophilic sulfur atom of thianyl chloride. The tetrahedral intermediate will collapse, and we now have this highly activated alcohol. Your carbonyl carbon will be attacked by the weakly nucleophilic chloride ion. And from here, we're going to kick out our activated leaving group, generating our desired acyl chloride. One important thing to note is typically when you prepare an acid chloride from the corresponding carboxylic acid, you typically do this under slightly to strongly acidic conditions. Any questions on the mechanism for this reaction? Any questions that I can address? Okay, so let's try to apply what we've learned here, and let's try to predict the products from the following reaction and draw a mechanism for the following reaction. So in this case, we have a carboxylic acid. In this case, we have butanoic acid, and we're treating it with thionyl chloride. So I'd like us to take a few minutes to read through these reaction conditions, and then let's try to predict the product from this reaction and propose a reasonable mechanism for this reaction. And if you have any questions or proposed responses, don't be shy to share them in the chat, verbally, or annotated directly onto the class whiteboard. So, would anyone like to propose a mechanism for this reaction? So we have the student drawing out the first step where our carboxylic acid attacks the sulfur atom in thionyl chloride. Perfect. Our nucleophiles attacking the electrophilic sulfur atom. Yeah, from here we'll make something that resembles the tetrahedral intermediate in carbonyl substitution, except this time the site of reactivity is our sulfur atom. Now, thionyl chloride is so electrophilic, and it's great because it has two wonderful leaving groups. So what's going to happen at our sulfur atom? So we currently have this intermediate that reminds us of a tetrahedral intermediate. And this intermediate will collapse and will kick out our leaving group, which is chloride. From here, we now have this wonderfully activated carboxylic acid, which can then be attacked by a range of viable nucleophiles. Would you be able to draw out the rest of this activated carboxylic acid?
Wait, I think I got mixed up. I don't know.
No, it looks fine so far. So now
Okay.
we have our carboxylic acid been activated with thionyl chloride. We have this pretty activated carbonyl carbon, and we have a nucleophile, not a very strong one, but it's strong in the context of this reaction because we have such a reactive and such an activated carbonyl carbon that even weak nucleophiles such as chloride will attack the carbonyl carbon. From here, we have our tetrahedral intermediate now. And in this case, when our tetrahedral intermediate collapses, and when it collapses, we'll kick out our better leaving group, which is the activated alcohol. This gives us our desired acyl chloride that we can isolate as a neutral product after one more deprotonation step.
Okay. I
Yep.
got it.
The student proposed mechanism looks perfectly reasonable. So let me clear this mechanism and then redraw it as part of the instructor solution. So we have our nucleophile, which is our carboxylic acid, and we have a wonderful electrophile in the form of thionyl chloride. So the first step, the carboxylic acid will attack the electrophilic sulfur atom. From here, this intermediate will collapse and kick out an equivalent of chloride. From here, now that we have our activated carboxylic acid, an equivalent of chloride will attack the carbonyl carbon. And now we have this tetrahedral intermediate, which will collapse. And rather than kicking out chloride, we'll kick out this activated alcohol. This gives us our desired acyl chloride, which can be isolated after a cleanup deprotonation step. The student proposed mechanism was completely reasonable. Does anyone have a question on this proposed mechanism? Any questions that I can address? Okay. So let's keep going then. And let's look at a case where we have a carboxylic acid, but we have an internal nucleophile. And let's just take a moment. And let's think through and let's just get a sense of which of these two species. So if we had to compare an alcohol to chloride, which of these two species is a better nucleophile? Which of these two species is a better nucleophile? An alcohol or chloride? So if you had to pick, for example, if we compared methanol versus chloride, what's a better nucleophile? Methanol or chloride? Generally, is chloride a good nucleophile? Generally, is chloride viewed as a good nucleophile? Is chloride thought of as nucleophilic in most cases? Not really, not really. Let's do another comparison, right? If we thought of methoxide, for example, versus chloride, what would you say is the better nucleophile? Which of these two species is the better nucleophile by far? Methoxide or chloride? Methoxide, right? Generally, oxygen-centered nucleophiles are better nucleophiles than your halogens. Halides are typically good leaving groups and poor nucleophiles. Part of the reason why they're such great leaving groups is because they're not very basic and they're not very nucleophilic outside of cases where you have super activated substrates. Does that idea make sense to everyone? Does this idea that methoxide's a better nucleophile, generally alcohols are better nucleophiles than halides, does that idea make sense? Well, the oxygen atom, in general, if we look at a typical alcohol, the oxygen atom has a large amount of electron density. A lot of the electron density is localized onto your oxygen atom, and it's held in a relatively localized orbital. So the lone pair on oxygen is more reactive than on chloride, bromide, or iodide, where the electron density is distributed over a larger orbital, right? We talked about this a lot in terms of nucleophile strength and leaving group strength in Organic Chemistry 1. Now, does that idea make sense? So why am I bringing it up in this case? Well, in this case, we're looking at treatment of a carboxylic acid with thionyl chloride, but we have an internal nucleophile. So in terms of the mechanism for this reaction, just like always, we have our carboxylic acid and we have our alcohol. The carboxylic acid will react with the electrophilic sulfur atom of thionyl chloride. From here, we'll kick out an equivalent of chloride. And we're back to the same intermediate that we've seen time and time again, where we have this highly activated carboxylic acid derivative with this great leaving group. Okay, now, if we had to pick a nucleophile to attack our carbonyl carbon, from our previous discussion, would we use chloride or internal alcohol? Considering as well that intramolecular reactions are substantially faster kinetically than intermolecular reactions. So what should we use as our nucleophile? The alcohol, right. So this internal alcohol will attack the carbonyl carbon. And from here, we'll generate 1, 2, 3, 4, 5, 6. The following tetrahedral intermediate. Now from here, if we had to pick a leaving group, to kick out, which leaving group will leave? Do we have an activated leaving group to kick out?
Wait, how is it 6 sides? Wouldn't it be 5? Or
The 6th atom is the oxygen atom.
oh, yeah, okay, sorry.
Does that make sense?
Yeah.
Perfect. So now that we have the following intermediate, which leaving group are we going to kick out? What's our best leaving group in this case? So when we think about thionyl chloride based mechanisms, this activated alcohol that reacted with thionyl chloride to make this chloral sulfide ester is highly activated. So then we can easily just kick out this leaving group. And there are many ways that we can kick out this leaving group. Let's just draw the easiest, where we just kick out the leaving group. And from here, we now have this ester. And then we're just going to do some cleanup steps where we pull off these protons. And that'll give us our desired cyclic ester, and we call these species lactones. The main point of this example is that when using thionyl chloride, you can activate your carboxylic acid, and then from there, you can take that activated carboxylic acid and react it with further nucleophiles in the same reaction vessel. So, as we've seen, we've talked about many common carbonyl substitution reactions. We've talked about how to prepare acyl chlorides from carboxylic acids and the utility of these reactions in organic synthesis. Does this example make sense to everyone? Does this make sense? Okay, so let's keep going then. And let's talk about the conversion of carboxylic acids into acid anhydrides. The first method, which generally requires very high temperatures, typically in an autoclave, is preparing acid anhydrides via direct heating to remove water. That's why anhydrides are called anhydride, without water. So if you take acetic acid and you heat it to 800 degrees Celsius, you'll get acetic anhydride. Not necessarily practical on the benchtop for small preparative amounts, but maybe useful on larger scales. You can also prepare anhydrides from an acyl chloride and a carboxylic acid. In this case, what is our nucleophile? So in this case, we have the acetate anion, and you can think of this as an alcohol equivalent, or even more aptly, a hydroxide or water equivalent. The acetate anion, although not the most nucleophilic species, is sufficiently nucleophilic to react with and attack the electrophilic carbonyl carbon of an acyl chloride. From here, we'll generate a tetrahedral intermediate. And in this case, our best leaving group is chloride. So we'll kick out chloride and we'll get our desired anhydride. Does this mechanism make sense? It's another textbook carbonyl substitution under basic conditions. And the beautiful thing about this process is that it allows you to prepare mixed anhydrides. Does this make sense? Any questions on this mechanism? Another way to prepare anhydrides is by using a substoichiometric amount of thionyl chloride, in which case you generate a small amount of your acyl chloride, which immediately reacts with your carboxylic acid. From here, just like before, the tetrahedral intermediate will collapse and kick out chloride. And with that, we're able to isolate our desired anhydride. The thionyl chloride method is only useful for preparing symmetrical anhydrides if you use substoichiometric amounts of thionyl chloride. Does this mechanism make sense to everyone? And does this synthetic process make sense? This is often why, if you want to get exclusively the carboxylic acid, if you wanted to exclusively prepare the desired acyl chloride from the carboxylic acid, you need to use an excess of thionyl chloride in most cases. Any questions on this example? Okay.
Oh,
So,
I
yeah.
sorry, one question. What is the significance of the 0.5 equivalent? Just like for the molar ratio?
Yes. If we use a half equivalent of thionyl chloride, approximately half of our carboxylic acid starting material will be converted to the acyl chloride, which can then react with the other half of remaining carboxylic acid to make one equivalent of anhydride.
Oh, okay.
If we use an excess of thionyl chloride, then instead we just get the acyl chloride and it would stop there.
Okay. Yeah, that makes sense.
Does that answer your question?
Yes, thank you.
So this is another method outside of direct heating to prepare these kind of symmetrical anhydrides, which are probably the most common anhydride substrates that are used. Yes, and the neutral product is the final product. Did that answer your questions? Perfect. So anhydrides react very similarly to acyl chlorides. They're a little less reactive, but not by much, in that anhydrides will react with most common nucleophiles to yield substitution products. So for example, if we have acetic anhydride and we react it with a common nucleophile such as ethanol, our nucleophile will attack the electrophilic carbonyl carbon, and yes, we can attack either carbonyl carbon, but for symmetrical anhydrides, it doesn't matter. From here, we'll generate a tetrahedral intermediate. And then this tetrahedral intermediate will collapse and we'll lose our great leaving group, which is acetate. From here, our desired neutral ester will then be isolated after deprotonation of our product. Typically, a basic amine such as triethylamine is utilized. You wouldn't want to use a secondary or primary amine. Typically, the basic amines used for these kinds of acylation and esterification reactions are typically tertiary. Would anyone like to comment on why triethylamine is used as the base in this case? Would anyone like to comment on why triethylamine is used as the base in this case, while something like ethylamine would not be okay? What's a problem with using something like ethylamine for this reaction? If I wanted to prepare this ester from an anhydride, why do I have to use a tertiary amine? And one student's commented in the chat, because ethylamine would react as a nucleophile. Exactly right. So typically we want a non-nucleophilic base just to scrounge away and get rid of any excess acid produced over the course of the reaction. Does this mechanism make sense to everyone? It's almost identical to the acyl chloride carbonyl substitution mechanism. Any questions on this mechanism? Okay. So let's take what we've learned now and let's try to predict the products from the following reaction and draw a mechanism for this reaction. So in this case, we have a secondary alcohol reacting with acetic anhydride and triethylamine. So let's take about 3 to 4 minutes and let's try to work through this example. Let's predict the product from this reaction, draw a mechanism for this reaction. And if there are any questions that I can address to help advance this discussion, don't be shy to ask them in the chat or verbally. And I'd like students to share their responses in the chat, verbally, or annotated directly onto the class whiteboard. So let's work through this example, and I'd love for students to share their responses for this question. So, would anyone like to propose a mechanism for this reaction? Would anyone like to propose a mechanism, or would anyone like to draw a structure for the product from this reaction? Is there a question I can address to advance our discussion as we work through this example? So we have a nucleophilic alcohol, we have an electrophilic anhydride, and we're working under neutral to mildly basic conditions. So what's going to happen if we have a nucleophile and an electrophilic carbonyl carbon for our anhydride? So we have a predicted product of our acetylated alcohol and the acetate ion. Would anyone like to try to draw a mechanism for this reaction? We have these predicted products. Would anyone like to justify these product predictions with a mechanism? So in this case, our nucleophilic alcohol will attack the electrophilic carbonyl carbon of the anhydride. Perfect. From here, we get a tetrahedral intermediate. So what's going to happen next? No worries. And if anyone would like to try to take the mechanism that this first student has drawn and carry it forward, you're welcome to do that. There's also plenty of space on the class whiteboard to share your own proposed mechanism. And I'm also checking the chat if anyone has a photo of their written work that they'd like to share. The stereochemistry doesn't explicitly matter, but it's mainly to highlight the fact that only the alcohol is reacting. The carbon the alcohol is attached to does not react and doesn't undergo any change in stereochemistry. So would anyone like to try to draw out the mechanism for this reaction? So we have the first step drawn where the alcohol attacks the carbonyl carbon. We have a student sharing their proposed mechanism in the chat. Let me check that one moment. And we have another student beginning to annotate. The mechanism that I see shared in the chat looks completely reasonable. Yeah, that worked great. And we have a student who's taking off where the other student left off and is trying to draw the remaining part for the mechanism for this reaction. So we last left off where our alcohol attacked the carbonyl carbon. We ended up with this tetrahedral intermediate. We have a methyl group here, so I'd just note that in the structure. Perfect. And now when our tetrahedral intermediate collapses, what's our best leaving group? The alcohol or acetate? Sure, you can show the deprotonation step where like triethylamine pulls off this proton. That's reasonable, sure. But
Have to be triethylamine, or could it be the anion, the acetyl anion? That's what you showed in the previous step, isn't it?
it can, but we haven't made it yet. That's why.
Oh,
yeah,
wait.
Because
I thought we just made it.
Not
That
yet.
wasn't that the leaving group?
It is, yes, but we haven't yet kicked it out, right?
Oh, yeah,
Because,
sorry.
because the leaving group hasn't yet left, it couldn't function as a base yet. That's why if you're showing the deprotonation step first, you'd use triethylamine.
Okay.
Does that make sense?
Yeah.
Perfect. Okay, so when we kick out our leaving group of acetate, could we check the substitution on this carbon? So we kicked out our leaving group. So what's left on our carbonyl? So right now we have too many substituents on this carbonyl. So what's remaining on the carbonyl after we kick out this leaving group? So we had a methyl and acetate and we kicked out acetate. So just the methyl group is left. Exactly right. From here, we can pull off a proton to get our neutral ester product. Perfect. Though the acetate just pulled off a proton. So I would just clear this, and this final product looks perfect. So the mechanisms that I've seen from the class so far, both annotated and shared in the chat, look reasonable. let's just re-annotate this mechanism as part of our instructor solution. So, as always, we have a nucleophilic alcohol and we have an electrophilic anhydride. Our nucleophilic alcohol is going to attack the electrophilic carbonyl carbon. And from here, we'll get a tetrahedral intermediate. This tetrahedral intermediate will collapse to kick out acetate. And one thing to note is that the reaction only occurs at the oxygen. So the stereochemistry is not altered over the course of this reaction. From here, as a last cleanup step, acetate will pull off a proton and we'll get our neutral isolable ester product. So we can prepare esters from alcohols and anhydrides, just like we can prepare esters from alcohols and acyl chlorides. Does this make sense? Any other questions on these examples? Okay, so let's keep going now, and let's talk about another way to convert carboxylic acids into esters. In this case, just like we've used acetate in the previous example as a nucleophilic species, we can also prepare carboxylic acids via an SN2 reaction of a carboxylate anion with a primary alkyl halide. This is a textbook SN2 reaction where our nucleophilic acetate ion displaces our iodide leaving group. Now, although the acetate ion is a subpar nucleophile, it can be used as a hydroxide equivalent for base-sensitive substrates. So in this case, your acetate ion will displace your leaving group in a textbook SN2 reaction. And then to free up your alcohol, if you don't want to just keep this ester group, you treat this sample with sodium hydroxide. In this case, hydroxide will attack the electrophilic carbonyl carbon. We will generate a tetrahedral intermediate. And then from here, we'll kick out our leaving group, which in this case is our alkoxide fragment. And that gives us our desired free alcohol after quench. This synthetic procedure is quite common in cases where you have a substrate that is sensitive to strong bases, but can tolerate weak bases such as acetate. Does this idea and does this reaction between carboxylate derivatives such as acetate and electrophilic alkyl halides to prepare esters, does this reaction make sense?
So there is the inversion of stereochemistry.
Yes, because it's still a textbook SN2 reaction.
Okay.
The main distinction is that in this case, by using acetate, you can react substrates that would typically undergo elimination when a strong base is used. Does that make sense?
Yes, thank you.
Perfect, perfect. Okay, so let's try to apply what we've learned here, and I'd like us to predict the products from the following reaction. In this case, we have a primary alkyl chloride, and we're treating it with acetate ion, which is a reasonable nucleophile. Let's take a few minutes, and then let's try to draw out a mechanism for this reaction and predict the product from this reaction. So let's take a few minutes to work on this example. And if there are any questions that I can address as we work through this example, don't be shy to ask it in the chat or verbally. And I'd like students to share their responses in the chat, verbally, or annotated directly onto the class whiteboard.
Professor, sorry, for the last example, what was used to protonate the alcohol
Just
or the
water,
oxygen? Just water?
really anything added during the quench.
Okay, thank you.
We have one student commenting, is acetate going to attack our carbon? Yep. And what kind of reaction will happen? So we have a nucleophile and a primary alkyl halide. What do we call this reaction? Between a nucleophile and an electrophilic carbon with a great leaving group. What type of reaction is this between our nucleophile and our electrophilic carbon? What's the formal name for this reaction? Or what's the formal name for this nucleophilic displacement reaction? What do we call this reaction? Just an SN2. Yep, exactly. And the reason why I asked about that is because it determines how you draw the arrows. So the attack of our nucleophile and loss of our leaving group occurs in a concerted fashion. That in turn gives us our desired ester. Whoops, one more carbon here. There we go. And here's our desired product ester. Not too bad for this mechanism, right? Does this mechanism make sense to everyone? Perfect, perfect. So let's just do a little bit of critical thinking here, and let's try to explain why the following reaction does not yield the desired product. Why does this reaction fail miserably? So we have a tertiary alkyl halide, and we're treating it with acetate. Why does this reaction not work? What's the problem with this reaction? Exactly right. The tertiary substrate, we primarily see E2 is preferred over SN1 or SN2 in this case. So in reality, once we have this elimination product, if we wanted to prepare this product, there are many ways that we can do that. We can do oxymercuration to get the alcohol. And then if we wanted to install this acetyl group, what conditions would we want to use? If we wanted to install this acetyl group, we have an alcohol, we want to install this acetyl group, how would we do that in this alternative route, in this new route that we've developed to get around this elimination issue? If we see elimination when we try to do this direct displacement, we've now gone through and prepared this alcohol. How do I acetylate an alcohol? What conditions do I use? What conditions? So how about base with an acyl chloride? What specific acyl chloride in this case? If we want to install an acetyl group, thionyl chloride is used to activate carboxylic acids. So it wouldn't work quite well in this case. You'd get elimination if you add thionyl chloride. But if you use, for example, acetyl chloride and triethylamine, yeah, these conditions will work great. And that would give you your desired acetylated alcohol. Does everyone see the limitations of this reaction and ways to get around those limitations? Does everyone see how to apply these methods to prepare esters and other carboxylic acid derivatives, and how each method has certain limitations? If you want to run a substitution reaction, your substrate can't be very hindered. Does that make sense? Perfect. Any other questions on this example? So here we found a route. We found it didn't work very well. We proposed an alternative route that accounts for the desired chemoselectivity. So what we'll do is we'll stop here for today. Are there any questions before we close out today's session? If we don't have any other questions, what we'll do